set. Okay. Uh, Good afternoon, everyone. My name is Hal Finkel. I'm from Argonne National Laboratory's Leadership Computing Facility, and I'm going to be talking to you about some work that we've been doing on OpenMP. The goal of this work is to teach LLVM's optimizer to understand OpenMP, and I'm going to talk to you a little bit about that, but in some sense I'm going to mostly tell you why we want to teach LLVM's optimizer to understand OpenMP, and what are the benefits of doing so. All right. And I should start by saying that the work that I'm going to present is mostly the product of Johannes Sofert, who is a postdoctoral researcher at Argonne, who works on my team. All right, good. This works. Okay, good. To explain why we want to teach LLVM's optimizer about OpenMP and what that means, first let me start by explaining how a compiler implements OpenMP. Like what does that mean and how does it work? So first here I have a very simple example, and this example has a for loop over here. Oh man, I can't point on this thing anyway. So it's a for loop, and and above the for loop there's an OpenMP pragma. So that pragma is going to be transformed by the compiler into, well, something to do with parallelism, obviously, right? That has to happen somehow. And so the question is, how does that work? And here I'll have an example. I'm going to come back to that in a second. So what happens here is that when the compiler generates code for this pragma, what it's essentially doing is it is taking the code that's inside that parallel loop, and it is somehow putting it into a separate function. And that separate function is then being called by the OpenMP runtime library on multiple threads. And that's how the OpenMP implementation implements this OpenMP pragma. So what happens, however, is that this process of taking the code kind of out of the function in which it resided originally and moving it into this separate function, while necessary in order to make it run in parallel, also has some undesirable side effects. And so what happens is that there are optimizations. So in this particular case, for example, there's an optimization that we would call constant propagation that might be inhibited by this transformation. So here I have a very quick example, and the outputs here are conceptual, they're pseudocode. But what's going on here is here we have this value of y here in this example, and it's set equal to some constant number. And then later on, you see we're calling these various functions with y, and nothing changes y in this case. But what's being shown here conceptually is that once the compiler moves the code there into this other function and calls it through the runtime library, the compiler kind of internally loses track of the fact that nothing is changing y, and so stops doing this constant propagation. So this is just sort of one of many examples of one of the kinds of things that can happen when you do this. So there are other ways of dealing with this. For time purposes, I'll sort of skip this. But this is one of these inhibitions, optimization inhibitions that is triggered by the use of OpenMP, which is why, as you may have seen on the title slide of the talk, the subtitle here is "Why does sometimes adding OpenMP slow down my code?" And this is, it's one of these kind of dirty secrets of, HPC benchmarking, right? Is that oftentimes, people will compile their code with OpenMP or some other kind of parallelism enabled. They will show you how that code performs on, one thread and two threads and four threads, etc. And the secret is, however, that if they had turned off all the parallelism and run it on one core, it would have been faster than maybe the one-core version with parallelism, but also the two-core version with parallelism, and maybe the four-core version with parallelism, right? And then, at some point the parallel version would have been faster, but it may not be, quite as nice as the results indicate. Okay. So here let me talk about another thing that we've been looking at. This is this problem with implicit barriers. So here I have a function, and this function has a OpenMP4 loop on it. Here I have another function. This function also has a for loop in it, and again, there is an OpenMP pragma that has a parallel region, and that has a for loop work sharing directive in it. And these things will cause the iterations from these loops in order to be to be split up among the various threads, and they'll all do their various pieces, and all of that seems to work pretty well. And one thing to realize, however, is that there's a barrier that takes place at the end of all these loops, because each thread, by default, does its part of the iteration space, and then it stops, and it waits for all the other threads to finish their parts of the iteration space, and then, only then, will it keep going. So, what happens is that, in the original code, see, I put all these pragmas here on top of these loops, right? But these loops are actually in functions, and those functions are called by some other piece of code. That's generically what happens. And so here's an example of something that happened. This is from one of the benchmarks. I'll show you later. And here I have some loop that has a number of iterations in it, and it calls a number of functions, and each of these functions can have OpenMP inside of it. And so what happens is that, conceptually speaking, each of these has OpenMP, but as I said, the OpenMP has these barriers at the end, and that's something that you have to keep in mind, because the barriers, like each time the threads will have to kind of stop and talk to each other, that adds overhead, and conceptually speaking, you may want to get rid of that overhead. So here's the problem. So first, so here I have these functions here, and the first thing you might say is like, well, the compiler may inline these functions because maybe they're in the same translation unit or using LTO or what have you, and that's a good thing to do. So now the code, conceptually speaking, looks something like this. So, I took these things instead of these functions, I now have these loops directly in the code. But, the pragmas and such are still there, and the barriers those pragmas imply are also still there. All right, so now I've gotten rid of the function call overhead, but generically speaking, thread synchronization overhead is much larger than function call overhead, so you haven't necessarily won anything in that particular regard. Okay, so the next thing a human might do, so if if a human does this transformation to this by hand, the next thing they might say is, oh, well, here, for one thing, I can take the parallel regions, the parts where all the threads kind of have to wake up and get told what to do, and I can move that outside of this loop. So now I have all the threads running, and then they just split up the various pieces of these loops. And that's also a good thing to do, and that eliminates some, but not all of the overhead. And then on top of that, I want to eliminate the barriers. Now, the barriers you actually can eliminate by hand, and you can do this in a very easy way because OpenMP provides this no-wait clause that you can put on the OpenMP directives. That's a handy thing to use because it gets rid of the barriers at the end of this first loop and also the second, until there's only a barrier at the end of the third. So that all makes sense, and that's the compiler and the runtime will be quite happy because your overhead is low. Now the only problem, of course, is that this is not code that you want to maintain because you've now inlined all the functions into this big function, and it's really bad practice to take your entire application and put it in one function. So what you really want to do is have all these things in separate functions and nevertheless get the performance of this version. So the question is, how do you do that? And this is the motivation. Here's another example. I'll come back to that. Here's the motivation for teaching LLVM's optimizer about OpenMP, is that this transformation is something the compiler can do all by itself. And so it's really nice if the compiler then does this transformation all by itself, and the person doesn't have to do it manually. All right. So here's another example. Another code. In this case, there's a parallel region. There's a for loop. There's a master region up here for the printing, but in any case, this is a loop that gets split over multiple iterations. And so what we've done inside of LLVM, we started prototyping a number of different ways of teaching LLVM's optimizer about OpenMP. I'm not going to talk about the details I'm not going to talk about too many of the details, but I'll mention the following. So this teaching LLVM's optimizer about OpenMP kind of involves two different things. So one is teaching LLVM's optimizer about the fact that the runtime calls that dispatch these functions on lots of different threads, these are not particularly scary. In fact, they behave in a very well-known manner, and we can teach the optimizer what that is. And what that does is it allows the optimizer to take information from the sort of original parent function and propagate it into the functions that have these the parallel code in them. And this allows us to optimize better the code that's inside those parallel regions. And so this is a graph for this piece of code here. And what we found is that the optimizer has a really hard time optimizing this piece of code because right now, once it turns all of this code here inside this big for loop, once it takes this out and puts it in this separate function, it kind of loses track of the sort of properties of these arrays here that are being accessed, and that causes it to generate code that's much slower than it might otherwise be. So that's kind of unfortunate. But if we teach the optimizer how to sort of look through the transition from the serial to the parallel code, then we can get rid of that kind of overhead. And so here, this is a quick performance plot of the result of doing that in LLVM's optimizer, where here this blue point indicates the original, the performance of the original benchmark when compiled with full optimization. And then when we enable this additional OpenMP knowledge in the optimizer, we get a substantial improvement in the performance because now the compiler is not kind of impeding itself by doing this optimization. And there are a number of different possibilities here for how we can optimize it. This first jump here from here to here actually isn't due to any particular OpenMP aware transformation so much as it is teaching the optimizer how to keep track of this information about the array properties. And this enables other existing optimizations to kick in, and you get much better performance. Okay, so that's this jump. We can also do sort of other transformations for argument privatization, other things, and these also give a slight additional enhancement. Okay. So here's another sort of schematic of code that's in another one of these benchmarks. These are both from the Rodinia benchmark suite. So here we have two loops. These loops have OpenMP pragmas, which are, well, somewhat verbose because they have lots of shared and private variables. Nevertheless, we can apply a very kind of similar kind of techniques to this. We've experimented with a lot of different kinds of optimizations that we can perform in LLVM. These involve a number of different kinds of techniques and combinations of these techniques. So for example here, so the base here, this is the original timing. We also have versions where we enable this array property tracking, the alias analysis improvements, technically speaking, and those improve things a little bit. We can also combine those with various kinds of argument privatization and other sort of techniques in order to prevent the optimization of the OpenMP regions from impeding optimization of the sort of code that comes after that. And that provides a very nice improvement. We've also experimented with OpenMP specific optimizations. So those include things like taking adjacent parallel regions and merging them together to eliminate the overhead of having multiple adjacent parallel regions. We have then, on top of that, eliminated redundant barriers. So there are barriers in OpenMP, and then some of the constructs also have barriers. And when you combine everything together, well, you may have redundant barriers just the way the source code is, but often when you combine things like parallel regions together, you end up with lots of barriers that are now redundant. Right, so if you have a barrier and then another barrier right after it, you don't need two, you just need one, so you can get rid of the second one. And this actually has a measurable effect on the performance as well. So that turns out to be pretty important. And we've combined all these various techniques. And I mean, in this case, you can see that we get about an 8% speed up from various combinations of these optimizations. And that's pretty useful. Okay, so now I'll just go back quickly to the original example that we had. From a while ago. This is from the Rodinia CFD benchmark. And again, we have these various functions, and inside these various functions are these various parallel regions. And we have an optimization that then does this particular transformation automatically. So it takes these things and it will combine the parallel constructs. It takes the parallel region and moves it out. And now here you can see what the effect of that is on the performance of the program. So again, here the base is the original timing. And various combinations of these optimizations improve the performance. And so overall, this is about a 12% performance increase over the original benchmark performance for that application. Okay, so that's for this data set anyway. Okay, so that's true. We've repeated these experiments with lots of other benchmarks. You can see that you get performance increases on many of them. So for the rest of the benchmark suite, for instance, this benchmark is 10% speed up. This one gets a 3% speed up. Okay, so these are not particularly interesting. Moreover, this is a Pathfinder benchmark. I think that's a graph algorithm. That's a 17% speed up. And so this is what we get from teaching the optimizer about OpenMP. And again, that means a combination of two things. One is sort of letting it look through OpenMP constructs so that existing optimizations can do the things that they're meant to do. And the second thing is to implement OpenMP specific optimizations. And using those specific optimizations, we are able to do things like combine in adjacent parallel regions, eliminate redundant barriers, and other things which will specifically increase the performance of parallel code. So this is what we've been working on. This is in the context of LLVM, and we are in the process of contributing the components of these optimizations back up to the upstream LLVM project, so that everyone will be able to download them, take advantage of them for themselves. Okay, thank you.